Okay. Now what are the other big benefits? So we will talk about two important things. One thing is lot of things. So first thing that I will cover today is fragmentation. Number one is fragmentation. What is fragmentation? This is an operating system concept, we will come to that. 2, intra-process protection. 3, inter-process protection. 4, security. So 4 important aspects we need to study as a part of segmentation. These are the 4 things in addition to the position independent compilation. So compiler had an issue and that is already solved. Okay. Now these 4 are basically operating system issues, and how will segmentation address this is what we are going to talk about. Okay. Now let us take this. I am now working with a big server. Okay. Now I have process 0's code P0, one minute, sorry, P0's code is here, P1's stack is here, sorry, P0's stack is here, P0's data is here. Let me call this 1000, 1050. So this starts from 0, 1060, 1090. Okay. Right. Now so let me say total is 1200, 1500. Okay. Total memory is only 1500. Let's just for now I have P2 code, P2 stack and P2 data. So let me say this is 1100, 1150, 1175. Now this is P3 code, so this is 900, P3 data and P3 stack, let us say 1290. Now, now this entire thing is hold that P1 code, stack and data are held in this. Okay, let us see. So this is how the memory is. There are 4 processes, P0, P1, P2, P3, and this is how these things are loaded. Please note that when P0 is executing, P0, P1, P2, P3. So let us see. Let us also have P1 will be 12, code will be 1290, stack will be 1300, data will be 1400, something like that. Okay. So when P0 is executing, CS will be 1000, SS will be 1050, DS will be 1060. Now when I want P1 to execute, when P1 is executing, this will be 1290, 1300 and 1400. When P2 is executing, it will be 1090, 1100, 1150. When P3 is executing, it will be 0, 900 and 1175. Are you able to follow? So when I move from, so what will happen is today when you log into your Gmail server, right, suppose your friend also logs in, both should be given some fair amount of service. If I say I will attend to your friend then to you, then what will happen? Till you will never log out, you will never log in. Okay. So it is basically what it means that when you click something, something happens on your screen, your part of the program gets executed. So when I open, there is a session open, there is a process created for you in the mail server. When he enters, again a process is created for him. So both these processes are given some time on your CPU. So I will give you some 5 units of time, whatever that unit, throw you out, then give him 5 units, again give you 5 units, 5 units. So both of you will have some feel that you are being served. So this type, so I am allocating a process to a CPU. So this is basically called as CPU scheduling. And this you will learn extensively in your operating system course, right. So that means what? Your process also started executing, her process also has started executing, both of these processes are loaded into memory. Then what I need to do is, I need to switch from one process to another process to another process to another process and again come back and do. This type of a scheduling is called round robin scheduling. While Robin is that Robin Hood, right. So who said a fellow should not have all the money, took away the money and then distributed to the poor, right. So something like equal distribution, all those things are attributed to Robin Hood, right. So this is also equal distribution, that is why this name round robin algorithm, right. So what is round robin? So I'll execute, I'll allow you to execute for some time, pull you out, then allow her program to execute, then the next one. So P0 will be given some time, it will be pulled out, next P1 it will be pulled out, next P2 it will be pulled out, P3 again say P0, P1, P2. So like this a round robin will happen, okay. You will learn lot about scheduling, and especially the Linux scheduler, the FAIR scheduler of Linux is very interesting. This you will cover very deeply in your operating system course, right. But what you should understand is the architecture has to support this. So when I move from him to him, one process to another process, that is actually called as context switching. We will read more about context switching here. Context switching need to be understood at the computer organization level, yes, so that when you go to operating system, you say I switch from this process to another process, you will immediately appreciate what is context switching, right. So we have one dedicated assignment in this course which is for context switching, which will just deal context switching, right, what it means to switch context, and there are a lot of security implications there. We will also cover those things in great detail, okay. Now in this case of context switching, for me it becomes easy with segmentation, because when I want P0 to execute, what I need to do, I have to load 1000, 1060 and 1015 to the respective register. When I pull out P1 and I want P2 to execute, what I need to do, just go and change the segment register value. I need not go and change anything in the memory. I load everything into the memory and keep all the process that are, all the programs that are in execution, namely the processes, all its data, stack and code, I can load it in memory and keep. Whenever I switch from one context to another context, I have to just go and change the value of the segment registers, right. So context switching means switching from one process to another process. The context switching essentially becomes extremely simple. So segmentation helps you in that context switching, okay. Now what will happen is, the next thing that segmentation will also do is that so what do you want, this is just the base address, right. So now I will go and say I will have 50 bytes here, I will have 10 bytes here, sorry 10 bytes here, I will have 30 bytes here. What is this 50, 30 and 10? Are you able to see? Color is good, okay. What is 50, 30 and 10? Limit, correct, this is a limit. So along with the base I will also store the limit. so that if this P0 fellow goes and starts executing beyond 50 bytes, right, if the offset is more than 50, that means I am going to access something. Okay. So the limit, I store the limit so that if I go outside that limit, then I am doing something wrong, correct? I should not go outside the limit. When the program compiled, it said I need only 40 bytes for all the instructions, sorry 50 bytes for all the instructions. So I have given that 50 byte. You start more than 50, if you go and say I want more than 50 bytes, then what will happen? Right? Then I am wrong. I do not have an instruction beyond 50 bytes from start, okay, because my entire code segment was only 50 bytes in size. Are you able to follow? So if I try to execute beyond 50 bytes, or if I go and access data beyond 30 bytes in this case, as you see here, or if I am going to access the stack, if I am going to go the stack beyond 10 bytes, then somebody has to catch you and say, hey, it is wrong. The operating system needs this help from the architecture, right, because otherwise what will happen is he will come and peek into your mobile into your mailbox, and he can take your assignment, because it is your data segment. Your mailbox is your data segment, so some friend of you can take it and submit it as his assignment and say you copied from him. Okay, all these things are possible. So essentially I need to save one fellow's data segment from another fellow's data segment. Okay. So if I am going to access anything beyond my capability, beyond what I am allocated, then I should be caught. Who will catch me? The architecture should catch me, not the operating system. How can the operating system catch? There is only one CPU that is executing, your program is executing on it. Operating system is also another software, it is not executing, it is dormant, correct? So when you are doing something wrong, the operating system is not even existent, right? It is dormant, it is not alive, it is not having control over the CPU. There is only one CPU. In that CPU your program is running. The operating system is resting in the memory. When P0 is executing, P3 let it be the operating system, it will be resting in the memory. Are you able to follow? Right? So if P0 does a mistake, the operating system can never catch it on its own. So it will request the architecture, hey Baba, if this fellow does some mistake, please tell me. Right? Raise an exception. Okay? Right? So along with your segment register base, I also store the limit, and if and that is given, and when the program is executing, it either crosses the limit of either of these three segments, code, data, stack, then immediately the architecture will raise an exception and the control will be transferred to the operating system. If you go and do a mistake, hey stop, it will catch your neck, pull you out, put the operating system in and say, sir, caught by miss, right? So this fellow has done something wrong. I am just bringing back your LKG memories, okay, right? This fellow has done something wrong, so take this. Got it? Right? So that is what we call as intra and inter process protection. I cannot overgrow my stack. For example, if this fellow overgrows his stack and start writing into the data, please note here, I am putting the pen here. If this fellow moves from the stack, P0 overgrows his stack and writes into data, that is also corruption. If P0 starts executing from the stack, it keeps executing instruction after instruction and he starts executing from the stack, that is also corruption, right. So intra process protection also I give you, and P0 cannot go and access anything beyond what it is assigned, 1000, 1050, it can't execute beyond 1000 to 1049, it can't access data beyond 1090, 1089. So these two things are basically ensured, these three things are basically ensured by segmentation, okay, right. Now we will talk about security last. Before that I want to tell you, let us say now P2 finishes, so P2 process is over, so P2 goes out, So, this memory becomes free, okay. And let us say P1 P3 also finishes. So, this memory also becomes free. So, what is the total memory available? Total memory now available will be, this is 1090 to 1075 would be 75 plus 1085, right, 785, yeah, sorry, 1290, 1090, 200, no, 1200, okay. Oh, okay. So, totally I have 2200 bytes of memory. Suppose I am getting now a fat process P4 which is asking for 900 CS, okay, and 900 CS and so 400 DS and 900 stack, sorry, 500 DS and 900. Okay. Now, what will happen is I have 1000 here, so I can put one CS here, I can put CS here, so I will have 100 bytes here, okay. Now, the remaining I need 1400, I have only 1200 here, okay. No, sorry, this can be 400, yeah, 900 CS, 900 SS and 400 DS. So, I can put 900 there, I will have 100 bytes left here, I put 900 here, I will have 300 bytes left here, 900 I can fill it here and I can fill 900 here, okay. So, I will have 100 and 300. So, I have 400 bytes available, but that 400 bytes I cannot allocate to CS, DS. I have allocated CS here, I have allocated SS here for 900 and 900 bytes. Now, there are 400 bytes are free in the memory, but they are not in contiguous space. You getting what I am saying? Yes or no? Right? So, I can't allocate that 400 because I need it to be contiguous. So, what I need to do, now I do something called, the operating system suddenly finds, hey, there is so much empty space, but I can't give that contiguous space. So, then it goes and does something called garbage collection, okay. Demeaning, right? Suppose your program just executed just before it, and now the operating system calls it garbage, okay. Okay. Now, what is garbage collection? Now, what I will do is I will put this P node to this, I will move it by 1000 bytes. Okay. So, this will, when I move it, it will fix off at, it starts from 1000, it fixes at 90, so 90 bytes, okay. Now, I will move this 1100 and sorry, this 1290 I will go and compact it with after 90, so 91 I will move this, what, this entire P1, okay. P node and P1 when I move, then immediately I will get lot of contiguous space, I will get the 2200 bytes which I can use it for P4. So, what it means to move this P node CSD out, just copy these contents there, and then what I will do, I will make P node CS as 0 and 50-50 remains the same, this fellow as 50, okay, because this moves to 1050 moves to 50, and this data is 60 and stack will be 50. I need to go and change these values. First thing is I copy everything from here to there, and then what I need to do, I have to go and change the value of the segment registers. After I change the value of the segment register, please note that the program will execute correctly. Now, I need not change your compiled executable, still what will happen, sorry, your 4 will remain 4. In the previous case it was that 4 was 1064, now it will become actually 4, now where is the data segment 60, it will become 64. Initially it was 1064 when your data segment was here, right. I will not go and change the organization of the data, this organization of the data is not changed, nor this executable is changed. I just copy it and just go and adjust the value of the segment register, everything works perfectly. Are you able to follow this? So this particular concept is actually called process mobility. What do you mean by process mobility? I will be in a position to move the process anywhere in the address space. This entire 0 to 1500 is called address space. So I will be in a position to move the code, the data, track, anything, anywhere. But that entire segment should be in contiguous memory, but segment can be placed anywhere. And code need not follow data, data need not follow code can be in Timbuktu, data can be in Kodu, Agudu and Cherry, and stack can be in Palghat, no problem. It can be anywhere in your address space. Okay, you understand? So I need not even maintain that contiguity between segment, but one segment has to be in some contiguous locations. And I can just adjust what I need to do, I can put it anywhere and just go and change the value of the base of the code, data and segment registers, that is all. Nothing more. Yes, 1 minute. So this is basically process mobility, and this is very much important from the operating system point of view, especially this is the terminology used in operating systems, what we call as degree of multiprogramming. What do you understand by the term degree of multiprogramming? It is the number of processes that are simultaneously admitted for execution. Number of processes admitted for execution. You are getting this? So now there are 4 processes admitted. And as I keep on admitting more and more processes, like every session can be a process, then I have millions of processes in a server, right. Then one important thing that the operating system needs to do at regular intervals is garbage collection. So when I want to do this garbage collection, then probably I need to do, I need this position, I need segmentation. Okay, you are able to follow, right. So yeah, coming to doubts, yes.
So if there is a pointer pointing to some location in the data, and then we copy the contents and move everything, what will happen to that pointer? The address will change.
Wait, we will come to that. I will finish this, then I will answer this. This is a programming question, I will answer that. So 4 things: fragmentation, intra-process protection, inter-process protection, security. Okay, all these things are clean. Now let us go. Now no, security is not clean. Why do you nod your head? Right, so we will now talk more about security. Okay, now before going to security, we should understand that operating systems are built in layers, right. So typical layered operating system looks like this. I think I have covered this in one of the earlier class. Layer 0, layer 1, layer 2, layer 3. Layer 0 basically has the kernel, layer 1 layer 1 actually has the system software, layer 2 has middleware like compilers, etc., and layer 3 are the application programs or user programs. Typically operating system can be these layers. The kernel has the highest privilege, the application program has the lowest privilege. Highest privilege means what privilege means what it can do. It can't go and shoot somebody, right? Privilege means that it can access what? What do you mean by privilege? What do you mean by privilege? No, it's not priority for execution. Privilege is, so what do you mean? Permission to what? Do what?
Access to hardware.
Access to resources, right? The exact name is access to resources. So the kernel, which is L0 at level 0, which is the highest privilege, will have more access to resources and more power in terms of I will again say more access to resources, while as I go from L0 to L3, the access to resources will start diminishing. So the numerically lowest privilege 0 is the highest privilege or highest power privilege, right. So Intel, based on this x86, based on this type of an organization, this type of a view, came out with 4 privilege levels. You could ask me why 4, right. So 4 privilege levels came because of this type of a tiers that we see in the operating system, okay. So answer is why 4, you will ask this question. Yes, you should ask this question. So this is the reason, okay.